welcome to lecture number 38, and we are discussing about one of the very important problem in circuit analysis, where there may be not only capacitor inductor, but there may be coupled inductors having mutual inductance between two or more coils, and then how to analyze such circuits. So, to do that we have to we have defined earlier, which have been discussed in my earlier class, but I will quickly tell you what we did last time. Suppose you have got two coils with N1 and N2 turns wound on a common magnetic circuit like this, and this is suppose N2. Then we and this is coil number 1, this is coil number 2. Then we showed that M12 mutual inductance is equal to M21, and we will call it M. And recall that L1 was defined as flux linkage when this coil carries current I1, total flux linkage, that is I phi T1 into N1, flux linkage with coil 1 when 1 ampere flows through coil 1, that is per unit ampere. Similarly, L2 was defined as phi T2 into N2 divided by I2, when second coil will be energized with current I2. That was how. And then we told you that this phi T1 has got two components, phi M1 and leakage component into N1 divided by I1. Similarly, this phi T2 will have two components, the mutual flux plus phi L2 divide into N2 divided by I2. This was the thing. And the mutual inductance between 1 and 2 was defined, that is due to phi M1, and this part of the inductance first term I call this LM1 and this is leakage inductance 1. Similarly, L2 is LM2 magnetizing inductance plus LL2. Up to this we have done. Now, if obviously, you can see that this inductance, the total flux linkage from this, for example, we can also say that total flux linkage is nothing but L1 into I1. Got the point? Similarly, flux linkage in coil 2 because of current in coil 1 will be phi N2 into phi 1 is not N2 into phi M1, and is the flux linkage when coil 1 carries current I1. What is the flux linkage with coil 2? It will be N2 into phi M1, because phi M1 is the mutual flux phi M 1 or 2. So, N2 into phi M1 is the total flux linkage, that divided by I1. I was telling M21 or M12, but we have established that these are same. So, M. Therefore, also note that the flux linkage with second coil. So, L1 I1 will give you flux linkage, total flux linkage with the first coil, and M into I1 will give you flux linkage with coil 2 when coil 1 carries current I1 and vice versa. So, inductance into current will give you flux linkage in Weber turns. So, this was the basis of the thing. Now, if both the coils carry current, if both the coils carry current and if I 1 and I 2 are constant, then of course, there will be no voltage drop between these 2 points, L 1 d I 1 dt will be 0. Similarly, the induced voltage in the other coil, which will be M d I 1 dt, that will be also 0. Therefore, now let us see what happens in time varying case. When coils carry time varying current. So, the first coil, consider first that the first coil is carrying current. Okay. So, these are the coils and this is the second coil and this is having N 2 turns and this is having N 1 turns. Suppose we pass some current in the first coil, which is some time varying current I 1 t, and the direction I have shown like that. Then the question is, this coil will produce a mutual flux, which is phi m 1, which that too will be time varying. When this current is maximum, phi m 1 will be maximum. When this current is negative, phi will be negative. So, this phi m 1 and I 1 in phase, phi m 1 and I 1 in phase, they will change. Therefore, this flux, which is going to link second coil, is a time varying flux, mutual flux. Therefore, we expect that there will be some induced voltage in the second coil, is not? That is what Faraday's law is. That is, the if in a coil perpendicular to its section, if there is a time varying flux, these two terminals will become a seat of EMF, and the value of this EMF will be N 2 and the rate of change of flux, that is phi m 1 t. This will be the induced voltage between these 2 points. So, that is the thing. Okay. So, phi m 1 t, and this can be written as d dt of I will come about the polarity. Okay. What will be the instantaneous polarity of the voltage, but before that what I do, I push this N 2 which is constant inside. So, it is N 2 into phi m 1, is not? This will be the thing, but N 2 into phi m 1, N 2 into phi m 1 is nothing but m into I 1. Therefore, I will write it as d dt of m into I 1 in terms of mutual inductance, and this m is constant and this m can be taken outside and I can write this. Got the point? Therefore, if there is a time varying current in the first coil, we immediately come to know that between these 2 points there has to be an induced voltage. So, also there will be an induced voltage between these 2 points. How much will be the value of this voltage? This, if I call it E 1, the induced voltage will be d dt. Now, I am writing in one stroke into N 1 phi T 1. If it is phi T 1, it must be L 1 I 1. This is, mind you, this is N 1 into phi T 1 for self inductance. Total flux linkage, how it is varying, across these 2 points, that will be this one, and this L 1 being constant, it is L 1 d I 1 dt. Okay. Now, if you see, let me call these 2 points as A B and these 2 terminals as C D. As I told you earlier, this whole thing, I will not now draw the elaborate diagram. Across A and B, I will conclude that there is a, as if a source of EMF present, and this is the direction of the I 1, and the polarity of this voltage will be this side plus this side minus, and the value of this voltage is L 1 d I dt. I mean, the story is this: second coil is not carrying any current, mind you, there is no current in the second coil, no current in this second coil, in this second coil. Under that condition, what is happening I am seeing. So, this is this one, and then in the second coil also there will be an induced voltage M d I 1 dt. These 2 terminals will be C D. If your I is time varying, I 1 is time varying, then this C D voltage available across C D must be also time varying. With respect to time, it will change. Now, the question is that if I assume this current direction is I 1 and d I 1 dt is positive, d I 1 dt is greater than 0, suppose current is increasing, then the induced voltage is such that Lenz's law tells us that the polarity of the induced voltage will be such that it will try to oppose the cause for which the current is due. Now, for which current is due? Current is due because you must have applied some voltage of this polarity, it is flowing in this direction, and the polarity of this voltage L 1 d I 1 dt is positive. So, upper one must be plus, so that it will try to oppose the cause, so that current increases, d I 1 dt is positive. So, this only it can do it by making the upper terminal plus and lower terminal minus. Therefore, the polarity of the induced voltage in across this coil, that is across A B, what I have assumed? I 1 is positive and d I 1 dt is greater than 0. These 2 things I have assumed, and then I will say polarity has to be like this, because current is trying to increase, but Lenz's law tells me the polarity of the voltage should be such it will oppose the cause. Current increasing means flux increasing, because I 1 and phi t 1 are in phase, and the coil will try to see that the change of flux which is causing the induced voltage is not allowed, it tries to keep that. So, upper one plus and lower one minus, that is the thing. Similarly, now the question is, with this being known, I ask ourselves that okay, that is fine, then how do I decide about the polarity of the induced voltage? So, V A B is equal to L 1 d I dt, L 1 d I 1 dt, that is fine. Similarly, here the voltage is M d I to dt. Now, what should be the polarity assigned to C and D? There are only 2 possibilities, either C is plus, D is minus, or this is minus, this is plus. One of them is correct. At the instant when A is plus, B is minus, at that time we ask ourselves, whether C is plus D is minus or C is minus D is plus. That is what we have to decide upon. Now, once again the decision is taken on the basis of Lenz's law. Lenz's law tells me that the polarity of the induced voltage in this coil also will be such that if it is allowed to act upon this EMF, the consequent current that is going to flow through the second coil should be such that it will try to oppose the increase in flux, because I have assumed d I 1 dt is greater than 0, that means flux is increasing with time. Therefore, it will try to see the whether plus or plus, that I will decide that if that EMF circulates some current, when you connect some external circuit to it, it will try to oppose that change in flux. Now, how it can do it? Got the point? So, I will just draw simply like this. This is coil 1, N 1, here is I 1 flowing. Now, there is coil 2. What I am telling? This magnitude of the voltage is now known, m d I 1 dt. But only thing I want to know that this is C D, whether. So, for that what I am telling, if this EMF, it is ready with that EMF, whether you draw current from it or not. But the polarity of the induced voltage will be such that if you happen to connect some say load across C D, imagine that resistance is connected, then it will circulate some current in the second coil, and this current should oppose this flux phi m 1 at that instant. Now, as I told you, there are only two possibilities, either this one is plus or this one is minus. Let us assume that okay, maybe the instantaneous polarity of the induced voltage across C D is like this, suppose. And if this voltage at that instant is allowed to act upon some circuit you have connected here, it will circulate current like this, it will circulate current through some resistance say like this, and the direction of the current here will be like this. And if this is the direction, look here, the direction of the flux produced by the second coil will be in the opposite direction. Your thumb's rule you apply. Okay. So, wrap the direction of the current. So, it will be like this, this way, and therefore, it will try to oppose this phi m 1. This is the flux created by the second coil. Therefore, it opposes the flux. So, this must be the polarity. The other one cannot be, that also I will tell. Suppose the other one is true. So, if the other one is true, this is plus, this is minus, the polarity of the induced voltage across this, then the current would have flown like this and direction of the current will be then just opposite in the coils, and the direction of the flux will be then from top to bottom, and which will be in the same direction of phi m 1. So, then it is going to strengthen the flux. Is that clear? So, polarity of the induced voltage of the which terminals is plus, which terminal is minus, is decided by Lenz's law, and I have explained to you how to find this out. Okay. Therefore, with this idea in mind, I will say that this I will cross out. There is only one answer unique. If this is plus at any instant of time, this is minus, and d I 1 dt is positive, the polarity of the induced voltage will be this is plus, this is minus. Clear? So, A and C terminals will have same polarities. Okay, after some time this will become plus, this will become minus, because you are applying a say time varying voltage. So, also at that time D will become plus, C will become minus. So, this is instantaneous polarity of the induced voltage, instantaneous polarity of the induced voltage, the induced voltage. Now, one important thing you just try to understand. This I remove it. Even if you do not connect that load, you while arguing this thing to decide upon the polarity, imagine there is some now current here in this direction, which will ensure this is plus, then you can come to the same conclusion. But what I am now trying to tell, that if in this diagram the core is drawn and then the coils are drawn with their senses, how in which sense the coils are wound, you can feel, you can easily understand. Instead of drawing like this, for example, somebody draws coil like this. I mean, somebody has a habit to draw coils like this. From this diagram, I will not be able to tell, at least on pen and paper, it is very difficult to say if this is plus, this is which one is this is plus, this, because I am not whoever has drawn these coils, he has not shown the sense of the winding. I understand very clearly what does it first go to the front end, then to the back, then front, then towards the back it comes out. So, this is called the sense of the winding, sense of the coils are known, both primary and secondary. Then on pen and paper, I know what is the instantaneous polarity. Or suppose somebody draws the coils they draw without showing, henceforth in fact, we will not draw the magnetic core, what is the point. But if you draw coils like this, two coils with terminals A and B, and this is C and D, and if at any instant this is plus minus, from the supply voltage I know the polarity, I know this is plus, this is minus, but here also it will be difficult for me to tell at that instant which one is C, whether C is plus or C is minus, it will be difficult. Although there will be only one terminal plus at that instant, and that I can decide provided I know the sense of the winding. Understood this point? Anyway, so this is the thing. Now, henceforth, so people, what people do is this, while showing the mutually coupled coils, they will draw coils in this way and put two dots here like this, and these dots indicates that if at any instant of time this is plus, the other one will become plus. It also means at any instant of time, if this is minus, at that instant it will be minus. But how these dots have been arrived at? Okay, for the first time you must know the sense of the winding and so on. We will show you later how by doing experiments You can also determine the very simple experiments one has to do to find out the to put the dot markings here. And people will write like this is self inductance L 1, this is self inductance L 2 and the mutual inductance between the coil is M. So, dot convention is the word, important word, dot convention, which conveys to us that instantaneous polarities of the input side voltage, primary side voltage and secondary side voltage, first coil and second coil, they will vary with unison plus plus minus minus like that. For example, let us draw another circuit, another magnetic circuit just to harping on the same point, but it is very important. People have lot of confusions in understanding. Suppose somebody draws coils like this, sense of the windings are known, but it is drawn in this way. Suppose I call this is A, this is B and this is C, this is D. In this case, if you say that at any instant of time the current is I 1 here, the induced voltage in this will be M d I 1 dt across C and D, that is fine, and I put a plus sign here. I ask you where to put the dot, plus, instantaneous plus, where should I put? Once again I go from by the basics. If this is plus, suppose you assume only two possibilities are there, either this is plus or this is minus, suppose plus. If this is plus and if this EMF is allowed to pass some current through some secondary circuit, then the direction of the current will be like this. If this is the direction of the current, through D current must come out and this will be the direction of the current. Here of course, the direction of the current is known and the flux which is causing the induced voltage across C D, it is in this direction at that instant. Now, I find if this is plus, this is minus, then the flux produced by the second coil will try to strengthen this further, which is not allowed by the Lenz's law. Lenz's law tells that direction of the current in the second coil should be such that at any instant of time that it will try to oppose the very cause for which the induced voltage is due. And this very cause is phi m 1 is increasing in this direction. Therefore, the polarity of this is wrong and it must be of this kind. No, it must be of this kind. That is, polarity of the induced voltage should be this is plus, this is minus. If this is the case, then the current supplied by this coil to the load will be flowing like that, and through the coils it has to be like this, and then you can see the flux produced by this coil opposes this phi m 1, is not this time the flux is like this, and it will try to oppose the flux, and that is fine with Lenz's law. Therefore, if you say this plus terminal, you say this is dot, I must put this as dot, one of them is dot. Therefore, it is now clear that with the dot convention, we try to convey the instantaneous polarities of the voltages of the two coils. So, henceforth I will draw the coils just like that. This is one coil, this is one coil. In this coil, sense of winding is possible? No. But then I will ask that give me the dots. It could be like this also, or it could be like that also, depending upon the sense of the winding, as I have shown for these two cases. So, it may be shown like this, or it may be shown like this. So, in this circuit do not draw the, I mean people do not prefer to draw the elaborate magnetic circuit, coils, this that, only draw two coils and show the polarities. And you must understand that there may be another coil here, there could be another coil, another third coil E F terminal. Here also this F will be, if this is plus. So, three mutually coupled coils, dot, this will be dot and this will be also dot, sense of the winding is known. So, there may be coils which are more number of coils and all of them may be coupled, sharing a common magnetic circuit, and it may be written as this is dot, this is dot, this is dot, you do not worry about that. So, and it will be written as this is self inductance L 1, this is self inductance L 2, this is self inductance L 3. And these two coils will have a mutual inductance between them M 1 2 or M 2 1, M 1 2 M 2 1 are same. Similarly, these two can have a mutual inductance of M 1 3. M 1 3 is same as M 3 1, we have seen M 1 2 same as M 2 1. Here it is necessary not to write M, because mutual inductances may be different. So, this is how it will be indicated in the coil. Therefore, there may be many mutually coupled coils. So, in today's lecture, in this lecture we have considered a very important phenomena, that how to decide about the instantaneous polarity of the induced voltage when coils will carry time varying current. Because if the currents are constant, then there is no induced voltage. If I 1 is constant, M d I 1 dt will be 0, no induced voltage here. Therefore, we will continue with that in the next class. Thank you.